All right, I've got a bunch of announcements for you today. Um, I would like to mention we have offering you an extension on homework 2. I know there's been a lot of heat, there's been the fires, there's smoke, there's lots of stuff going on. People have mentioned power outages, so we're giving you a 2-day extension on homework 2. So the due date is this Saturday instead of this Thursday. Um, the you can still get an extra credit point if you turn in 1 day early. So if you turn in Friday, we have supplemental videos available on the course webpage. If you go to the resources page, we have extra videos. We've recorded a version of this, online version of this class for the world. And we have videos there that you can find if you lecture didn't work for you or you want to see it presented by someone else totally, other than us. Go take a look there. We've got videos that were recorded by Professor Anil Adhikari and John De Niro, who are two of the co-founders of this course and are amazing. They get you the same ideas, but presented by a different person from a different context. They may not 100% match everything we do, so I wouldn't recommend relying on them as your primary source or substitute for these lectures, but you're welcome to go use those anytime you want. We are not live streaming on YouTube today because it looks like we got plenty of room, so we don't need to live stream on YouTube. I'll post the lecture on YouTube after. Small group tutoring. We make small group tutoring available. We still have space available. If you would like to work in small groups or get more practice with problems, I encourage you to sign up for tutoring. Meetings have started and we got plenty of space available. I wanted to mention about our collaboration policy. I've noticed folks posting solutions, and I wanted to ask, please don't share your solutions. Please don't post your answers to the homeworks. Please don't post them publicly on Pata. Please don't post them on other discussion threads. You should never share your solution. You should never be looking at someone else's solution. You should never download a solution from a previous semester. I don't want you to get in trouble with cheating. Doing that runs afoul of our collaboration policy, could get you in trouble for cheating, and you'd be surprised by how effective we are at catching these things. And it's a really unpleasant situation for the student and for me. I don't want you to have to go through that, and I don't want to have to go through that either. If you missed a discussion section this Monday because of the holiday, you will not lose credit. And we have group office hours and we have space available, so come visit us. We'd love to see you. It'd be great to see you. If you want to talk about class stuff or you just want to talk about anything else, maybe data science related or whatever else is going on in your life. Okay, so that's discussions for today. Walk you through what we're going to do this week. We're working, we've been teaching about tables in a Python, and we're going to start showing you how to use these concepts to analyze data. And usually when you get a new data set, one of the first things that often we do is we do some kind of exploratory data analysis where we want to go understand what's there, start visualizing the data, answering some basic questions about it. So today I'm going to give you a little review on table, and we're going to do a case study. We're going to work with your responses to the welcome survey on homework 1. We're also going to work with data from the US Census. And Friday, we're going to start looking at how to visualize data, different kinds of visualizations. Okay. Table review. So let me give you a review. We talked about tables as our way of organizing data. As a reminder, this is a bunch of columns. Each column has a label. All the data within the column should be of a similar type. And columns, you can extract a column as an array. Each row represents a single individual or thing, like a state. We've shown you a number of methods for tables. These are operations you can do on a table. With column, we'll let you create a new table that adds an extra column. Read table will let you create a table from a spreadsheet. You can count the number of rows and the number of columns. You can refer to columns by either the label or by an index, a number. So for instance, with this example table, you could refer to the first column by the label name, or by a number, an index. Indexes count starting from 0. So this is column 0. Then the next column is column 1, and the last column is column 2. So the last column you could refer to by label, area M2, or you could refer to by index, index 2. Given a table, you can use the column method to extract the data in one column and get access to it as an array. And then you can use array operations to operate on that data, like take the average of the values in that column. We've shown you a number of different operations on arrays. Item will extract a single value from the array. Sum will add up all the things in the array. Min and max will compute the min and the max. Yeah, the syntax for accessing the first column in this sample array would be dot column quotes name, or it would be dot column 0. Either one would work. Anywhere that you refer to a column, you can either use a string that's the label, or you can use a number that's the index. Dot item does not work on a table, but you could use dot item on an array. Given a table, you can create a new table that has just some of the original columns using dot select or dot drop. So let's do a demo. All right, so here I've got a table that is your answers to the welcome survey that you filled out for homework 1, where at the end we asked you a few kind of random questions to give us some data to work with. So I thought it's always kind of fun to poll the class and understand stuff about us. So let's try working through a few things that you might want to do with this data. You can see in this data we have a bunch of rows. There's about almost 1,300 rows. Almost 1,300 of you answered those questions. Thank you. And each column refers to one of the questions that you answered. So extroversion numbers, higher numbers are people who are more extroverted. This is the number of texts you did per person. It's anonymized, so there's no names in there. Number of hours of sleep, right-handed versus left-handed. Which leg do you put in your pants first? So let's look at the sleeping position. Let's look at how many people, we could ask how many people sleep on their side. Let's do that first, actually. That's a good one. How would we figure out how many people sleep on their side? What table operation would be appropriate for that? Dot where, yeah, dot where would be great. We would do welcome dot where. And we want to find the people who sleep on their side. Well, that's on your left side or on your right side. So I guess we want either of those. So any answer that involves the word side. So I'm gonna use a predicate like this. That will find me the people who sleep on their side. And then we can check that out. Okay. And now to figure out how many of them there are, we do dot numRows. That would make sense. And there are 766 of you who sleep on your side. So a little over half of you sleep on your side. Okay, so now let's look at how we would figure out how long you sleep. For those of you who sleep on your side, how long do you sleep? And there we're going to take that table of those of you who sleep on your side, and we're going to get the data of how many hours of sleep you have as an array. So I'll use the dot column operation to do that. That gives me an array of data, and I want to know the average. So I'm going to compute that. Okay, so side sleepers among you sleep on average 7.2 hours. If we wanted to know how long those of you who sleep on your back sleep, we could do the same thing. Is that an option? I think that might have been an option. 7 hours. Okay. All right, so I see a couple of questions. How did I know to put the r dot containing in here? Well, there's a list of different kinds of, we call these predicates, filters you can use with where, and we could take a look at that list. I'll show you how you could find the list. We have a reference, so you can go to the documentation for the data science package we have. And here we have a page for the predicates, and it has a list of all the different possibilities here. So you can see, oh, so many of them. And r dot containing is one of the operations. And you could do r dot above, or r dot below, or r dot equal to, or r dot between. All right. Why do I use dot column and not dot where? Well, dot where gives me some of the rows. Give me the rows that correspond to the side sleepers. And then once I've got that, what I want to know is the average number of hours of sleep. So now I need to take the average of everything in this column. The way I do that is now I want to extract the column. So the way to do that is the dot column method. That gives me an array with the numbers 8, 8, 8, 8, 7, 8, 7, 7, 6. And I want to take the average of those numbers. And so I use an operation on arrays to do that. What about np.average versus np.mean? Well, let's find out. Suppose I do the same stuff, but I do np.mean. Same answer, and that's because np.mean is the same operation as np.average. They're just two different names for the same thing, so you can use either one. Yes, there's also a reference page, as Unite points out, with a list of all the predicates you can do. Between talks about if you have a number between 5 to 7. Not between means it's not between 5 to 7, and strictly has to do with whether you include the endpoints, whether 5 or 7 are allowed. Okay, let's do another example. Let's suppose that now I want to count how many students get at least 8 hours of sleep each night. I notice there's a lot of 8s in here, but also some lesser than 8. Some people think that maybe 8 hours of sleep is good. So let's figure out how to count how many students get at least 8 hours of sleep. Well, we'll start with a where operation to extract just the rows, just the respondents who get at least 8 hours of sleep. And for that, I need a predicate here. And I want not 8. If I put 8, that would give me the students who get exactly 8 hours of sleep. But that's not what I want. I want those who are at least 8. So, well, not above. Above would give me the folks who have 9 or 10 or 11. So I want above, there's an operation above or equal to that I looked up. That will give me everyone who gets responded 8 or a larger number. And that's a table with the number of with the students who responded 8 or larger. And I only care how many are in that table. And so I can do .num rows. And the answer is 467 of you get 8 or more hours of sleep. So a lot of you get less than 8. Actually, there's multiple ways to do this. Here's another way you could have done it. We could have instead extracted the column of all numbers in that hours of sleep for all the respondents. That would give me an array. In fact, let's look at that array. So that's an array with those numbers. And then I want to count how many 8s there are in that array. So here's what I can do. I can do an array operation that will just keep track of which elements are at least 8 or more. If I do that, then it tells me here's students true, true. There's at least 8, at least 8, at least 8. And then there's a false, someone who's not at least 8. And now I want to count how many of those are true. And there's a way to do that with an array operation. and bam. So the count non-zero works on an array and counts how many elements are not zero. And Python considers false to be zero and true to be not zero. True to is kind of like a one and false is kind of like a zero as far as Python is concerned. So that's another way of counting. Here's another way you could count. You could, instead of using count non-zero, you could actually do sum. And the reason that works is that false gets converted to zero and true gets converted to one, and then you add them up. And so when you add up the ones in there, that's adding the number of trues. That's adding the number of students who are getting at least 8 hours of sleep. Okay. What was the sample size of this survey? Well, it wasn't really a random sample. It was just a self-selected response. And we can see that about 1,289 of you responded. So 467 out of 1,289 get 8 or more hours of sleep. Those of you in this class. To create an array, the way you do that is not with np.array, but do that with makeArray. Okay, let's do another example. Suppose that I want a table that only has the number of hours of sleep and this position you slept in, but whether you're right-handed or left-handed doesn't matter, for instance. Well, we could do that using this code here, where we select just the columns for hours of sleep and the position you sleep in. And I renamed them. I renamed them instead of originally called hours of sleep, I renamed it to just hours. Maybe that's easier to type. The way you can do that is with this relabeled operation. And here this relabeled says relabel column index 0. That's this first column. Change the label to .hours. Give me a new table where the label's been changed to hours instead of hours of sleep. And change the label of the next column instead of sleep position to just position. That gives me a new table, and I'm showing you this new table. Yeah, I can zoom in. Sorry about that. My fault. Is that good? Tell me if you want me to zoom in even more. All right. So this is kind of handy. Sometimes if we download a spreadsheet from the web and the labels at the top of the columns or some really long string, and we kind of want to make it simpler, or it has some columns in there that are extraneous and not relevant to the exploration we want to do, then we can drop some columns and relabel them. We could have done the same thing in this alternate way, where instead of listing what columns we want to keep, we instead drop the ones that we don't want. All right, so what relabeled does is it creates a new table, but it just changes the labels up here, changes the labels. So let's do another example of relabeled. I'm going to show you, here's the original table. You can see those columns. Now, if I relabel hours of sleep column, maybe I want to give it the new label just hours. Then that will create me a new table where this label here has been changed from hours of sleep to hours. Yes, it makes a new table. It doesn't change the original table, which we can see if we display. The original table has left unchanged. So most operations don't change the original table. They don't change the data. They just create a new table for you. That's kind of handy. For instance, if you rerun the notebook, it won't make the same change to your data twice. So good style to create a new table. All right. In this case, welcome was the name of the table. Why did it get that name? Because I read the table in from a spreadsheet and I assigned it the name welcome. So with that assignment statement. Could you flip labels? I think you could flip labels with the .select operation. Play around with it and see if it works. All right, so let's continue. That's some review of tables and some example operations. Here's a few more operations you can do. Sort, we'll sort the rows of a table. And it'll put them in order by some column. You specify which column you want to use to sort it. you can tell it if you want it to be, by default, it'll sort from smaller to bigger numbers, but you could put it in the reverse order if you want. Dot take will keep some of the rows. If I want row number 2 and row number 3, it'll let me keep those rows. Beware that everything is, we're dealing with indices here. So row number 0 corresponds to the first row. Dot where, we talked about, keeps picks out just some of the rows that meet a condition. You can use it either some rows where one column has a specific value or where a column meets a condition. Okay, so we just saw a bunch of examples of those. I want you to try working on a problem. So let's suppose we have a table that has these 3 columns: player, position, and salary. And it represents players in the NBA, basketball players. All right, so challenge for you. Figure out how to create an array that contains the names of all the point guards who make more than $15 million a year. So the position column will have PG in it if they're a point guard. And the salary column will have their annual salary. So figure out what table operations you would use. Type it into a private chat message to me to show me what operations you would use to create an array like this. So show me the full code, not just the operation name, but show me the actual code you type into Python. Okay, good stuff. I see good answers coming in. Keep it coming. Great. Lots of good answers. Okay, so here's the answer that I got for you. I see a lot of good stuff coming for you. So there's 3 things you want to do. You want to make sure you have only point guards. So you need to make sure your answer includes something to include only the point guards. So you can use a dot where operation to pick only the rows that correspond to basketball players who are point guards. You need to make sure it only has those with salaries above $15 million a year. So you can do that with a dot where operation that filters on the salary. And you need to make sure, this is a piece that some of you missed, you need to make sure the answer is an array. So you need to convert this to an array that has the names. So I don't want a table, and I don't want a table with all 3 of this information. I just want just the names and then to put an array. And you can do that with the dot column operation. So here's sample code shown on the slides. There are multiple possible answers. You can do this all in one line by putting a where upon a where, NBA.where, position PG, dot where, salary R above, dot column. I did it on 2 lines to try to make it a little clearer what's happening. There's multiple ways you could do this. The dot column extracts a single column from the table, just the column with the names, and it turns it into an array. So we'll see this in a notebook soon. Let's do one more discussion problem. I want you to consider if I wrote Python code, these 2 lines of Python code, figure out what the result of the second one is, and type it into chat in a private message to me. All right, I see lots of 3s. I see lots of 2s. I see a few 1s. I see some 4s. Sweet. Okay, this turned out to be a really good discussion question. There was a reason I asked this. So, I bet you I can make a guess about what's driving your answer. If you said 2, you're probably thinking you started with 3 columns and then we dropped the position. So now you got only 2 left. Makes sense. But there's a little bit of an issue with that. Most table operations don't change the original table. Remember that? So NBA.drop creates a new table that has only 2 columns. We created the table. We didn't do anything with it. The NBA table still is what it is. So the NBA table still has 3 columns. So the second line of code actually returns 3. So if you returned 3, you got the right answer. That was a little bit of a tricky question there. Good job. Okay, all right. And if you said 2, I totally get where you're coming from. This is just to kind of highlight, this is something that could bite you as a bug in your own code, that you might get caught by this or confused by this. So if you had code like this, the fix would be probably that you would assign the result of NBA.drop to a new name. And then when you wanted to count the number of columns, you would use that new name instead of the name of the original table. Okay, so I saw some questions about this. So let's do it in a notebook. Let's do this code and see what happens. So I have loaded in this salary table from the NBA from, I don't remember, several years ago. All right, so the first question asked us to get all the point guards. So that's position point guard. And then that gave me the point guards. And then what I was going to do was I was going to extract those where the salary was at least 15 million. So maybe like this. I don't know. We didn't say whether exactly 15 million should be included or not. So it could have been r.above 15. There's a table with the point guards whose salary is above 15 million. Oh, there's only 5 of them. And then we want to convert that to an array. So we extract the column of the players. And now we have it as an array. Okay. And the second question I asked you was, I said, what if we did NBA.drop position? And then we did NBA. And as you can see, the answer is 3. And why is that? Because NBA.drop position outputs a new table that has just 2 columns. But NBA refers to the original table. The original table hasn't changed. Okay. End demo. All right, let's keep going. In a table, all the values in a column should be the same type and should be comparable to each other in some way. All right, so what do we mean by that? By a type, there's kind of 2 types of data you'll typically see. One type is called numerical data, and there each value is from some numerical scale. It's a number. That's what numerical indicates. And the measurements are ordered. So it might be number of inches, it might be your salary, it might be your weight. All of those can be ordered. Who's heavier, who's taller, who's got the larger salary. Taking the difference between 2 values is meaningful. He weighs 2 pounds more than I am. He's an inch shorter than I am. He makes $1 million more a year than I do. Those are numerical data. Categorical data is when each value is from some fixed inventory, some fixed list of categories. For instance, I'm left-handed or I'm right-handed or I'm ambidextrous. That's categorical. What's my favorite color? It's red or it's blue or it's green or it's yellow. There's a list of colors that's categorical. It's not numerical. There's no sense in which you can take red minus yellow and get some meaningful number. Zip codes would be a good example. Yeah, zip codes are categorical. I mean, they look like digits. 94720 looks like a number, but it's not actually the number 94,720. It doesn't have any meaning like that. If you subtract your zip code from my zip code, it doesn't mean anything. My zip code is a bigger number. It's not somehow cooler or awesomer. It's just we assign digits to these different zip codes. All right. All the data within a column should be of the same type. Like if you've got a height in inches for one person, it should be height in inches for all of them. All numerical within a column or all categorical within a column. Just because the values look like numbers doesn't mean the variable is numerical. Like you gave the example of a zip code. We're going to see an example working with US Census data where they'll have a column for the sex. So that could be either male or female. And it's represented by the number. Those were the only two options in the data set that we had. And those are represented by the numbers 1 or 2. Okay. Actually, 0 is also used, and that represents some of all people, but regardless of sex. Okay, so this would be a categorical value. It might look like a number, 0, 1, or 2 looks like a number, but it's not actually numerical. There's no ordering. There's no sense in which it makes sense to take the difference between 2 minus 1. It's a fixed number of categories. Letter grades, categorical, totally. Good example. Yeah, there's an ordering, but it's not really numbers. Now you could convert, I mean, letter grades are a little bit ambiguous. Maybe you convert the letter grade to a GPA with the standard scale, and now you got a number and you can consider that numerical. Yeah, so numerical grades would be numerical. Order numbers on a menu. I'd like item number 27. Looks numerical, but it's not really. It's actually categorical. You're picking from a fixed inventory of candidates. Okay, so let's look at some census data. I think it's kind of fun to look at real data sets. So this is data from the last census. Every 10 years, the US Census Bureau counts how many people there are in the US. And then they release aggregate information. Okay. In fact, the US Constitution requires performing a census every 10 years that counts everyone who lives in the US. And I guess we're in the midst of a census year right now, and there's a lot of, it's actually in the news about work to do the census this year. In between every 10 years, where they literally count everyone, they'll estimate how many people there are based on some statistical estimations, but they don't actually try to talk to or get a response from every individual person in the US. So the Census Bureau releases some data, some aggregate data. And we'll see one data set that we downloaded a while ago that has a bunch of different columns. In the sex column, there'll be information about, like, for instance, average age, or the number of people of a certain age group, or average salary, things like that. And they'll break this down by different categories. So some of it will be broken down by sex. So we'll have in those, if it's referring to only only males, then it'll have a 1 in the sex column. Only females will be a 2. We'll have a column which is the estimate in 2010 of the US population. I haven't grabbed a more recent data set. Some rows are sums of each other. So for instance, there'll be a row for where the sex column is 0, that's counting the total number of people regardless of sex. You'll have some rows that are counting the number of people of a certain age, but then they'll have another row which counts everyone regardless of age. So this is an example where you see these numerical codes are used for convenience, but it's actually categorical data, at least for the sex column. And values in the column have the same type. So, but there is some weirdness, right? Don't necessarily want to compare a row corresponding to people of age 12 versus the row for 999, which is people of all age. All right, so let's look at the data. work with a data set here. So we've downloaded the spreadsheet and loaded it into a table. This is a spreadsheet you can download off of their website. You can see all sorts of stuff in there. There's their 2010 census. This is their estimate, the best estimate of the population, taking into account things like response rate and so on. Then they have estimates for each subsequent year. We downloaded this data in 2014. Lots of stuff in there. Let's keep just 4 of the columns. And let's use some shorter labels on the columns. So we'll create a new table that has the columns relabeled. What does full.select do? The select operation on a table creates a new table that has just some of the columns. We wanted just the sex, age, census 2010 population, and population estimate 2014 columns. And the rest we don't keep. Partial.show and .show. Well, show is an operation on a table, so you couldn't write just .show. So for instance, if we added .show for, we would get a syntax error because Python says, hey, you need to provide us a table name. Tell us which table you want to show. So correct way would be partial.show. And the before the dot indicates which thing you're operating on. And then this is the name of the operation, and then this is the arguments to the operation. For means show me the first 4 rows for the .show operation. Could I have written full.select 0, 1, 2, 3? Yes, I could have written full.select 0, 1, 2, and then 6, 7, 8. That would have worked, but it would have been a little harder to read because you would have seen this number 8 here and you would have been like, which column is that again? I got to go count. It would have been annoying. So, all right, so we could sort this by the age row. And what is this showing us here? This is counting the number of people who are age 0. So this is the number of infants basically. And there were 3.9 million of them in 2014. And then there were about 2 million of those that are male and about 1.9 million. Wait, did I get that backwards? I bet I got that backwards. I bet that's 2 million that were female. Let's see. Oh, I had it right. 2 million that are male, 1.9 million that are female. Okay. And then you can see how many there are of age 1. There's 3.9 million that are of age 1 and so on. I can sort in the reverse order. So for instance, this will show me there were 161.9 million people in the US in 2014. And that has about 157 million males. Oh, sorry, I did that wrong. 318.8 million people in the US. And that's about 157 million males and about 162 million females. Women tend to live longer. And you can see here, the max they've got is for 100. There were 58,000 people who were 100 years old. Pretty cool. 999 is a special code that they invented for the people of all ages without regard to age. So we could have gotten that data without the 999 column by extracting all the other rows and then adding them up, but they did the addition for us. When the sex is 2, that means female. Male is 1, 2 is female, 0 is the sum without regard to sex. There was no one over 100. I don't know whether this is anonymization, whether they didn't include anyone over 100 or whether they, I don't know. That seems weird. Yeah, you would expect there are some people who are over 100. All right. Now we could visualize this data. Often it's helpful to visualize data. So let's take people. I wonder how the size of the population varies based on the age of the people. So let's take a look at that. Oh, I see comments saying everyone who's 100 and over is treated as age 100. Ah, yes. Good, good, good. You are paying attention. Thank you. Yeah, there's a mystery here. There are 42 million people who are 99 years old, and then 72 million who are 100? That seems weird. You would expect there to be fewer who are 100. And the answer is there are fewer who are 100. Anyone who is 100 or older, 101 or 102 was coded as 100. I forgot about that. Thank you. Yes. Okay. Very good. All right. So now I want to plot this data. You can notice that it's very hard to get a sense for what's going on in this data. There's a lot of rows in this table. I could show all of them if I really wanted to see everything. This, but look at all that data, all that data, all that data, all that data. Oh, so much numbers. It's like wall of text. It's hard to extract much meaning from that. And sure, I can see how the population size depends on age sort of by looking at individual ones, but it's hard to get a feeling for that because there's just so many rows in here. And I've got stuff that's cluttered up with both broken down by gender and by not. And I guess I could keep only the rows that show the sum without regard to gender. So let's do that. That would simplify it a little bit. All right, so now I can see how population size depends on age. And I can sort of visualize it. It looks like there's maybe 4 million or so who are young, and that kind of grows as you get to older people. There's kind of a bulge here where there's a little more people who are age, let's see, a bulge at around age 31 or 32 or something like that. And then, oh, it gets even higher at age 53, and then it starts dropping off. The population drops off as you get older and older. People die more and more. But it's still hard to understand, to get some sense of trends by looking at lots of numbers. And so often it's much better to draw a graph to plot this. So let's take that same data. I'm going to keep only the rows where the age is a real number. 999 isn't real. 999 represents, here's an extra row they added that sums up people of all age. That was for convenience for people who are viewing the data but don't have tools to add up the rows very easily. They don't know the coding techniques you use. So we're going to get rid of that row because that's not actual real. There's no person who's actually 999 years old. And then we're going to keep, we don't care about sex, so we're going to keep the rows that report the population without regard to sex. And that gives me a table, and we can look at that table. This has the population in 2010 and 2014. And now let's visualize that. So there is a dot plot operation, which will give you a graph. And the graph here shows on the x-axis, it shows the age, and it shows the y-axis, it shows the value in this 2010 column, which is the population, the number of people in the US of that age. So for instance, if we look here at 20 years old, we go up here, there's about maybe 4.5 million people in the US who are 20 years old, or were 20 in 2010. There were 4.5 million who were about 20 years old. So this now gives me a sense of population trends in the US. For instance, you could look at the demographics and you could see baby boomers in there. You could see years when the birth rate was high and the birth rate was low. You can see how things drop off as people die as they get older. You can maybe start estimating for pension planning. You can see how many people are 65 or older. You can see how many are entering the workforce. So this gives you a much quicker way to visualize patterns in the data. And on Friday, we're going to talk a lot about how to do visualization. All right, so let me check for a few questions in the chat. Can I plot both 2010 and 2014 on the same graph? Yes, there's a way to do that. And let's see if I can remember how to do that. Oh boy. Good test. I don't remember how to do that. I can't remember how to put them on the same plot. There is a way to do that. I think for now, I'll just put them on 2 separate plots. Ask on Piazza and we'll dig up how to do that. I know there's a way to do it. I'm just forgetting off the top of my moment. Is it possible to relabel the 2010 to say population? Sure, we have an operation called .relabeled that would create me a new table with a different label for that. So let's do it. There you go. So now you got the plot looking like you wanted. Instead of saying 2010 there, it said population. How would I graph multiple years? I'm sorry, I just forget how to do it off the top of my head. Ask on Piazza and we'll figure out how to do it. How did I get to everyone.plot, specifically the everyone? Well, I created a table called everyone right here. That's what I created. That's this table here. And then we haven't taught you about this yet, but one of the operations you can do with a table, we provide a method called plot. It's an operation that will give you a plot of the data in the table. And each row in the table corresponds to a point. So there's a row in the table for age 3 with 4 million as the value in the 2010 column. And so that will be plotted on this chart at age 3, 4 million. So there's a dot right about there. And each row in the table corresponds to a dot in this graph, and then it will join those dots with lines. And so we provide you multiple methods to do this kind of visualization. It's very helpful. We'll teach you more about that on Friday. What does the y-axis mean? The y-axis is, well, in this case, it was the 2010 population. So the census estimate of the population in 2010. So it means the number of people in the US of that particular age. Oh yeah, we can get both of these on the same plot. Thank you for the reminder, Yanai, about how to do that. If we don't provide a second argument, then it'll plot all the other columns. So here you can see how things change from 2010 to 2014. You notice the yellow curve is shifted a little bit to the right of the blue curve. Why is that? Why did I think that happens? It's kind of interesting, right? It's the same shape, but shifted over. Well, if you think about it, it makes sense because from 2010, blue is 2010, yellow is 2014, 4 years passed. Everyone got 4 years older. So if there were 4.5 million 20-year-olds in 2010, in 2014, they're 24-year-olds. So now there's 4.5 million 24-year-olds in 2014. So everything got shifted to the right. Shifted to the right and maybe a little bit lower because some of those folks died. And then you got some new folks who were born. Okay, we're about out of time. So that wraps up. So hopefully you've started to see how to do operations on tables. And what I want you to learn from this is you can use Python to combine these simple operations to do more complicated and sophisticated things. And then on Friday, what you're going to see is a beginning of us looking at how you do visualization, how you visualize data, which will be very helpful for exploring and understanding patterns and trends in a data set. I'll stick around after lecture if anyone has any questions. Thank you very much. Don't forget to go to lab this week, and we'll see you in lecture on Friday. Bye, everyone.